Hmm. Hello. Hello. Is it live? Yes, it's live. I can't see it on the thing, but okay. Okay, it is live. Mhm. Uh, yeah. Cool, 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 cool. Okay, let's just wait for a few more people to join. Then we will start. Let's just wait for a few. Okay, two people are here. Fantastic. So I did not, for the two people that are watching, I think one of them is me. Have to do it like this because last time PPT wasn't helping anyways. So this time we're going to do it like this. Anyways, I will wait for 5 more minutes. Then we'll just straight up jump into the code. Oh yes, hello. Yeah. Yeah. So we're gonna wait for 4 more minutes. We're gonna wait till 9:35. Then we will look at some code. We will look at some maths and all around try to have a fun time. Hopefully. Anyways. Yeah. So I don't know. Grab your sting, grab your drinks, whatever you have, and be prepared for some mathematics. I mean, not that much actually. This session is not going to be very math heavy, even though neural networks tend to have a lot more maths than last session. Bad internet. Do I have bad internet? Hello? I don't think so. I think the internet is fine actually. Um, okay. Yeah. Okay, a few more people have joined. We are gonna wait for 2 more minutes and then we will start. Okay? Yes. Man, I promised myself I wouldn't drink Sting so much, but here we are. Yeah, so I think we can already start. There's enough people waiting. Uh, Screw it. Let's just start. Whoever comes late comes late. Okay, so hello. Today is MLJams session 2, and we're going to be driving into neural networks. We're going to be driving into classification this time. We're going to find out. That's pretty fun. And then eventually, we're going to do the big thing. I mean, you can see the foreshadowing in this tab over here IMDb sentiment analysis with BERT, using BERT with Hugging Face. Sorry. Yeah. So, a lot of stuff to go through. Now, since ML session, ML Jam session 2 is about neural networks, we have to talk a bit about neural networks. So, neural networks is a very vast sort of topic, right? I think if you've attended the last session, we talked a bit about neural networks. I think I called it the cool kid of machine learning. And that's exactly what it is. It's the most important algorithm when it comes to machine learning. I mean, most important subtype of an algorithm when it comes to machine learning. Neural networks is the most modern, state of the art way we do machine learning in our modern lives because neural networks is part of something called deep learning. Deep learning refers to a large amount of data since data in our lives has been increasing exponentially. Data increase rate, yeah, data growth. Sorry. Data growth worldwide. Let's just look at images. Yeah, so we know that data has been growing worldwide and at an exponential rate, 175 zettabytes in 2025. Are you serious? Okay, that's a lot actually. Yeah, so 175 zettabytes of data will be generated by users worldwide in the year 2025, according to this prediction. Which, I mean, honestly, it looks right, so I'm not going to question the metrics on it. And we know about Moore's law. Moore's law means that about every 18 months, the amount of transistors you can fit in one sort of square inch doubles approximately. Yeah, the Moore's law is an observation that the number of transistors in an integrated circuit doubles about every 2 years. About two, yeah, okay. Moore's law is an observation or projection of a historical trend, blah, 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 blah. Okay, essentially what it means is that not just data, but our ability to compute that data has been increasing exponentially, which means there's a lot more we can do with our data now. And that's why machine learning and AI and deep learning and all these buzzwords that you hear are becoming more and more and more popular because now we can do things that we couldn't like 10 years ago or maybe even 5 years ago, right? So, what are we doing today? Why do we do deep learning, first of all? Because now that neural networks are becoming popular, we have to ask ourselves why are neural networks becoming popular? It's because neural networks perform better on a large amount of data and a large training set, essentially, what you call it. So, last time we saw linear regression, and linear regression and these small algorithms like linear regression, you have logistic, logistic regression, which is another classification algorithm. We won't be getting into this right now, but logistic algorithm is a simple and more efficient method of binary and linear classification problems. These algorithms, there's also support vector machine, which is another popular classification algorithm, SVM for short. And these algorithms are fine for normal day-to-day classification jobs. First of all, I think we should explore what classification is. Classification. So, what is classification? Classification algorithms are a supervised learning technique that uses training data to identify a category of new observation. What does that mean? Classification basically means that, let's say you're trying to tell the difference between a cat and a dog. That's classification. Let's say you're trying to tell whether a picture has a dog or not. That's technically classification. I mean, it falls more under the image object detection umbrella. But at the end of the day, it's classification. You're telling whether something is something or not. So, yeah, we have a bunch of algorithms that work out well for classification, right? You have logistic regression. Do not confuse this with linear regression. It's slightly different. You have decision tree, you have random forest, k nearest neighbors, blah blah blah, and all these algorithms are very fun once you get into the mathematics. But that's not what we're here for. We're here for neural networks. So neural networks allow you to do a lot more than just these specific algorithms. Neural networks are sort of more flexible with their application. So neural networks, you can do not just classification, but you can do regression, you can do reinforcement learning, unsupervised learning, supervised learning, reinforcement learning, and all that stuff we talked about in MLJams session 1. So now, uh, right, what else? So now we need to find out how neural networks actually work, right? So there's a lot of maths, okay? Like, okay, here's a video by Three Blue One Brown. I don't know if you know him, but it's a very popular YouTube channel about maths mainly. And Three Blue One Brown, this entire series on neural networks, does a great job at explaining the mathematics behind neural networks. And I strongly recommend that you watch this series after the session is done. All right, because then you sort of get a feel for what's actually going on under the hood, and once you understand the mathematics of an algorithm, you can implement it in whatever way you want, and you can sort of have your custom algorithms and maybe even figure out something new that someone else didn't know before. So I strongly recommend that you understand the mathematics first, and then go on to like actually write the code. So neural networks, I think we can explore the maths a little bit. I have a few articles up here, and I think we should explore that. So a general introduction to the math of neural. This is a great article. Uh, Please go check this article out. By Dasarid SK. Yeah. So we're gonna go through this article, and yeah. So what is a neural network? First of all, to boil it down to the bare minimum, a neural network is just a glorified math function. Okay, that's all it is. It's don't think of it as an algorithm first. Think of it as a mathematical function. It is comparable to like sine of x, cos of x, but just way more complicated. That's it. So don't be scared when you see the maths. It's mostly just linear algebra and calculus. The probability stuff comes in later. We'll see that as well. But yeah, it's mostly just linear algebra and calculus. Okay, lots and lots of both of those two. So if you didn't have fun with your courses last sem or last to last sem, depending on what year you're in, you might struggle, but I feel like it's a lot more fun when you try to apply it. Last time, when you were learning linear algebra, you weren't really applying it on anything. You didn't know the real world case. Well, here it is. Here's why you should know linear algebra. We're going to see why we use a dot product here. I hope everyone knows what a dot product is. Uh, yeah. And I mean, that's all it is. I mean, linear algebra, there's a bit of calculus here. Okay. Yeah, so last time we saw back propagation and optimization. That's going to be here. We're going to go here in a bit. We saw mean squared error. That's going to be a loss function, if you remember. If you don't, then I'll just tell it again. That was our cost function, right? Cost function and loss function. We're also going to descent. If you remember that, that was our major. That was essentially how the machines learn, right, through the gradient descent algorithm. So we're gonna go through that, and yeah. No spoilers. Let's just go through this first. So what is this article talking about? Today, with open source machine learning, we can create a neural network. We're gonna see TensorFlow in a bit. Okay, this is our main sort of framework that we're gonna go through. We can create a neural network even with high structural convolution. Okay, so first we're gonna look at perceptrons. Perceptrons were the first ever. So if you look at an image, perceptron, here, perceptrons were just a very, very simple mathematical function. Yeah. So here we see a perceptron. Now, if you remember from maths, let's say you have a function like y equal to mx plus b, right? Now, m and b were parameters. Similarly, here you have three inputs instead of x as last time, and you have three parameters, and you have x into w naught, y into w1, z into w2. All right, and if you put this in a matrix, you will sort of say that this is the input matrix and this is the weight matrix. There will be a bias here somewhere. You take the dot product of the input matrix, you take the dot against Okay. Yeah. Okay. 1 second. Be right back. 21. Sorry for the interruption, guys. Interruptions, multiple. But yeah, okay. Where were we? Yeah, so you take the input matrix and you take the output matrix. Sorry, the weight matrix. Weights are essentially a parameter. So what M and B were for y equal to mx plus b, that's your parameter. So that's what you do. You take a dot product and then you get the output. But in machine learning, we need to learn these weights, right? You need to know, okay, what will give the desired output. So how do you do all that? We will look just now. Yeah. So that's what a perceptron was. So see, here's what it's happening, right? This is essentially this whole thing. If we go here, this whole thing is essentially a dot product. Okay. X matrix, matlab, uh, the input matrix multiplied by the weight matrix, and all of it is getting added. So yeah. So you take the dot product, and this is how you can put in sort of the vectorized form. And you add a weight, and you add a bias. Now the bias is important because it sort of offsets the value in a way where you can properly fit the data set. You can Google, you can, I mean, research this later, why we use bias. But just know that since it's the same concept as y equal to mx plus b, b is your bias, it's your intercept. Anyways, so now you have this. This is our activation function. This function in particular, 1 divided by 1 plus e to the power minus z, this particularly is called a sigmoid, and it's an activation function. Now, what an activation function do? Let's actually look at a sigmoid. Sigmoid. This is a graph. This is the plot for a sigmoid. And what it's doing is it takes any value, okay, 0 to infinity, any value, and it maps it down from 0 to 1. Now, this is important. This is a very, very important step because, as you know, all probabilities go from 0 to 1, right? You can't have a probability of more than 100%. That makes no sense. So, to map it down, you do something called normalization. You map it down to 0 to 1, essentially to make sure that every single probability, because in machine learning, you only deal with probabilities, you can't give hard answers, right? So, because you're predicting stuff, you're not actually saying stuff. So, you only get probability from 0 to 1. That's why you keep everything from 0 to 1. That's why we use activation functions in every step of the way, just to keep it in a range. So, there are multiple activation functions. Now, you do 0 to 1 with activation function. This is sort of the intuition, but you have other activation functions like ReLU, which don't actually get it from 0 to 1. They just work like this. They just take any value that is negative and set it to 0, and anything above 0, they set it to whatever it was. So this does not actually map it from 0 to 1. And this has other applications. This also doesn't completely break the neural net. But essentially, activation functions introduce something called nonlinearity. I mean, it's a lot of maths for this session, so you can go through that stuff later. If you're doing a course, I think some people were mentioning Andrew Ng's course. Andrew Ng has very succinctly defined why we use activation function. Like he goes into depth. But this is just a study jam. This is just to go over the bare minimum maths of it all. But yeah, so we remember backpropagation from last time, I hope. Essentially, whatever error you got, you try to minimize it using gradient descent, right? You take the gradient, you use the loss function ka gradient, and then you reduce everything down. Like, yeah, see. So, yeah. So you have your activation function, right? Let's go back to that image. Yeah. So here in this purple circle, you are applying your activation function and then you get an output back. So यहाँ पे dot product, here you did dot product, put it through the activation function, and you get a out. Now from the output, you apply the loss function. So now you sort of made a chain, right? Excuse me. You sort of made a chain that inside this function can have this function, and you sort of get this. Yeah, you sort of get this, right? You know the chain rule. So essentially, you're trying to find gradient with respect to a certain weight. So according to this weight, like to optimize this weight, W naught, you have to find the gradient with respect to W naught, right? So that's what you do. You take the cost function. The cost function, inside that there's the average, and then inside that there's Z. So you can go through this math later. I'll put it up later. But yeah, so you find the gradient and then you reduce it down. You follow the gradient descent wala method that we explained last time, and you go through that. This is pretty standard maths. But yeah, and then obviously optimization. You set a learning rate. You set a regularization. We see that later. Yeah. So go through this article. It's very nice. You can go through it later and go through the playlist on YouTube of the Three Blue One Brown. So now, I think we can actually go into the classification. So we can go into the first code example. We're not going into the this thing yet, sentiment analysis. We're going to go through a smaller example of what classification actually means. Then we're going to go into sentiment analysis, because sentiment analysis is actually very heavy. There's a lot of concepts that you need to know before that. So we're just going to glance over sentiment analysis, and I'm going to explain you each part. But if you don't get it, that's fine, because there's a long road ahead. I'm just showing you what is possible with neural networks and what people can actually do with neural networks right now. So yeah, anyways, we're going to go through. Let's start this session. This is the Kaggle notebook, by the way. I think last time I used a Colab notebook. This is Kaggle. I find Kaggle a lot nicer than Colab, because Kaggle gives you free GPU access. It can give you a GPU. It can give you two NVIDIA T4 GPUs, or it can give you one NVIDIA GPU, the P100 series. So this is very good when you start training your machine learning models, especially neural networks. Because the thing with neural networks essentially is that there's a lot of parallel processing involved. Once you do matrix multiplications and matrix math, once you do matrix multiplication, matrix maths, you have a lot of parallel operations to take care of, right? Even in our sentiment analysis, you will see we'll be using something called a transformers algorithm. You have a lot of parallel processing involved, and GPUs are excellent for parallel processing as compared to a CPU. CPUs are great for series, like they can handle big tasks and just finish them off at once. GPUs can handle multiple smaller problems at once. So in machine learning especially, I think you've been seeing like NVIDIA and NVIDIA's whole machine learning sort of advantage over everyone else, that, since they make the GPUs, they sort of control the whole AI market. That's speculation. I don't know. But like, yeah, so GPU is very important. If you can get your hands on a GPU, fantastic. My current local system has a great GPU, so that's why I got into machine learning. Or I think I got this laptop because I got into machine learning. Either way, GPU, great. Not just for gaming, for deep learning as well. But yeah, so let's go into the code here. So last time we saw import. Let's make this a little bigger for you. Yeah. So yeah, screw that. Oh, we can do this. Anyways. So, oh, look, doggy. Anyways, yeah, so NumPy, so we have NumPy. That was our matrix multiplication, linear algebra, mathematical God library. We have pandas. So again, we're going to be dealing with CSV data. Last time we did stock data, that was in CSV format. This time also we're going to be dealing with CSV data, and we're going to look at the data set in a short while. So Now we have pandas. Pandas is to handle our data set. We have matplotlib. Do we need matplotlib? I don't think we need matplotlib actually. I don't know why I have it. Anyways, force of habit. I guess. Then we have TensorFlow, our big main fancy library that's going to handle every neural network related thing for us. It is a major framework. If we go to TensorFlow, one sec. Oh, okay. Something happening in the comments apparently. Yeah, no. Comments are not updating. Yeah. Oh, okay. Yeah. Say hello to my sister, everyone. Yeah, okay. So, oh, that is incredibly distracting. Yeah, so let's get back to TensorFlow. Right. TensorFlow is our major deep learning framework. It's going to help us build everything. Yeah, so go through the documentation. It is not the friendliest documentation I would say, but it gets the job done. So yeah, okay. This is very funny to me. Yeah, okay. Cool. So that's enough of that. TensorFlow. Then we have like sub utilities that we'll look at later. So now let's look at the actual data set itself. We're going to be exploring the iris flower data set. So the iris flower data set. Let's look at this. So going to the Wikipedia page, actually that's not the best. Let's go to the Kaggle, because everywhere you see you will have something related to Kaggle when you get into machine learning. Kaggle is a great place. It's a forum for machine learning applications, and you can you can do competitions here based on machine learning. You can get data sets. You can see other people's code. It's great. There's some of my work here. Let's not look at that. Okay. So yeah, the iris dataset is essentially a dataset of three classes of the iris flower. You have the iris setosa, you have the iris versicolor, and you have the iris virginica. Uh, yeah, okay. Cool. Yeah. So and these values, this dataset has four different values, four columns to determine whether a flower is a setosa, virginica, or versicolor. So you have sepal length, you have sepal width, you have petal length, petal width, whatever these numbers. I'm not a biologist, but all I need to know is just to take these numbers and see which class it is and to essentially predict which class it's gonna be. Cool. Yeah, TensorFlow, great. Yeah, so let's look at that. So we have here sepal length, sepal width, petal width, and species, right? If you look at the database dataset info, we have all this, I guess. If we describe, this is the count. So we have 150 values. We have 150 rows of each. Here is the mean sepal length, mean sepal width, blah, blah, blah. We don't really need this. I'm just showing it for the sake of showing it. So here is a sample. So using df.head, you can get the first 5 values. Anyways, yeah. So run this. Yeah, so essentially what we are doing here is we are converting. So df.species, we are converting this to categorical. So here's what it is, right? Species in this column is given in text. Like this is text. You can't do maths on text. I mean, not explicitly. Not like you can't just add two numbers and get a result, two strings and get a result like that. We'll actually see how you can convert text to numbers in a bit in this thing. But yeah, for this case, you can't actually do any maths on it, right? Like you can't apply the functions on it just yet. So what do? you use a pandas function as always, and you convert it to a categorical sort of you convert it to three different categories numerically. So if you look here now, we have essentially converted this to binary. Okay, this is now a binary vector. Uh, and now instead of so if you do y here, oops, sorry, let's restart that. Uh-huh. Oop. Oh, okay, sorry. df species. Yeah, so right now, y was oh yeah, for people asking about the dog, you can add dogs here. You can add cats, you can add dogs, you can add whatever you want. Yeah, so dogs, cats, very cute, very nice. As the session goes, there will be more. Hopefully, it's not too distracting. If it is, just let me know. But yeah, cool. Okay, so now you've converted it to uh, binary classes. Okay, so the first 50 values, that's our setosa. Setosa has been converted to 100. Versicolor has been converted to 010, and Virginica has been converted to 001. Okay, so now we can actually do maths on this. Now it's a vector, we can do maths on it, right? Cool. So now let's go through this state. Okay, now you wanna split your data set into train and test. Okay, how do you do that? And why do you do that essentially is the bigger question. So you split your data set, your entire data set will be split into train and test. So training essentially is what data set you'll actually use to teach your machine learning model. And test is once it's been taught, you will test it, right? Like you study for cats and then you go and give your test to see how good or bad it is. So that's essentially what we're doing here. So we're going to take 80% of our data set. 8 into 15 is something. 120. Yeah. 120 samples will be for training, and the rest will be for testing. 0.2 of the whole data set will be for testing. So 120/30 split, pretty standard. 80/20 split is pretty standard for most machine learning applications. Right, we've run that. And now we can look at the X train, and this is what it'll look like. Oh yeah, by the way, it's all shuffled up. So shuffling is important because you don't want to train like one whole class and then the other class just gets left out. You shuffle it so that you can keep your machinery model, sort of guessing like which one is next. Okay. So now, yeah, see 120 rows and 4 columns. This is what we've gotten. X test, X, Y. Yeah, so I forgot to mention actually. X will be everything except the species column, and Y will be only the species column, but converted to categorical, converted to like this binary vector. Anyways, so now we use something called scaling. Scaling essentially just fits everything to a value. So last time we saw in our stock prediction thing, we had to scale everything down so everything worked properly. Here also we use a standard scaler. Let's actually go through exactly what it does. Whoops. Let's copy this. Standard scaler. Yeah, so this is a utility of scikit-learn. Scikit-learn is another very helpful machine learning library. Yeah, so essentially it standardizes a feature and removes the. Essentially, what it does is keeps everything to a value which is, accessible to. Is essentially standardized. Is all you need to remember. But yeah, and then you scale it down. You scale the X train and the X test to whatever it has to fit. And then now this is our meat of the project. Okay, meat of whatever we're trying to do. We are defining a neural network. Now, there is actually a very good website for this, Neural Network Playground. It's by Google. Yeah, here. So here you can see this is a neural network playground. Tinker with a neural network right here in the browser. This is a very great website. If someone can put up the link for that, it'll be great. It's just playground.tensorflow.org. And here you will have. Okay, yeah. So here you can actually test out whatever. So we have multiple activation functions. We have like sigmoid here. There's regularization. We'll look at that later. Rate regularization, problem type classification. Yeah. Oops, excuse me. So in this problem, we're going to define a neural network. What is happening in the chat? I'm sorry, guys, for whatever's happening in the chat. But yeah. Okay, I'm sorry. Yeah, so coming back, this is very distracting. I don't know why we even opened the chat up. But yeah. Uh, so now we have four layers. We've defined four layers in the neural network. Uh, this is what teachers feel like when people in the back are making fun of the teacher. Anyways, okay. Yeah, so you have two inputs. In our case, we can actually have four inputs. And the second layer can have seven neurons. The third layer can have six neurons. This doesn't really matter. This is arbitrary for this use case, anyways. And then outputs, since you're trying to classify two classes, you can have two outputs. In our case, was actually three, but let's keep it at two for this use case. A lot of people are just roasting me in my chats, but okay. Yeah. So yeah. Now we can actually start training this. So we have set an arbitrary learning rate. We've set a activation function, and now if we start so if we go through the epoch, yeah, look, this and the classes start to begin, right? Color shows data and neuron. This is how essentially our neural network will learn, right? Yeah. So it's a technique, blah, blah, blah. You can go through this. Very, very fun. You can play around with it for hours. Wow, training loss is zero. Wow, this is very nice. But yeah, show test data. This was our test data. Yeah, train test, blah, blah, blah. So what if we added another? Okay, what if we messed around with the training test set? Okay. We add some noise. Let's add our noise, batch size 16. This is all you can see later. We can play around with this as much as you want. You can read up on all this. We can play around with this for a while. L2 regularization. This is also a very interesting concept. Regularization. You can explore this later. Essentially, we add regularization when your model is overfitting. And yeah. Okay. And then now we run and look. Wow. Fantastic. So cool, guys. It's amazing. Can you hear the joy in my voice? Anyways, yeah. What if we try to classify this? It's wow. I don't know how you're actually gonna show that, but yeah. Okay, I guess that's that. That's not very fun. Okay, let's look at this. Whoa, cool. I guess. Still getting roasted in my chats, but okay. I'm trying to be joyous. I'm trying to be joyous about all this. I'm just very hungry right now. Yeah. Okay. So let's get back to our own thing. So we have an input layer with four features. Our four features are sepal length, sepal width, blah 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 blah. Okay, and our initial layer, our first layer, has 128 neurons. Ooh, fancy. And our activation function is ReLU, as we saw before. We're going to be using ReLU, this thing. It's a good simple function, very simple to implement. It's essentially this, yeah, max 0 comma x, just to remove negative values. We don't have any negative values, so we can actually change this. But when I was experimenting around with it, Yeah, this is so distracting. But yeah, so now we have four inputs. We have 128 as our initial layer. We have something called dropout. We will look at dropout in a bit. Then our next layer is 64 neurons. This is just arbitrary. When I was experimenting with it, this is what I set. This is what I came up with for the best amount of accuracy. And then we have our another layer of 32 uh, neurons. And lastly, our last activation function was softmax function. This is standard, by the way. You can look it up later. Right now, I'm just going through as fast as possible for the sake of actually finishing everything that I've planned. So yeah, go through this notebook later. Then we have model.compile. Yeah, sorry, I totally forgot. So our model is essentially a sequential model. Okay, it's something called a feed forward neural network. So feed forward neural network, feed forward neural network. It's one of the most classic types of neural networks where feed forward essentially you do a forward propagation and then to optimize it you go back. So everything in a neural network, let's go back to this image. Yeah. So you feed information from here, it goes forward from left to right, goes forward, and you get an output, right? You do the matrix multiplication in a forward direction. And then that's why we call it back propagation. When you're sort of optimizing it, you traverse back, right? You find the output error, you go back, you fix these weights according to what the error was, and then you go to the next input, sorry. So that's essentially what it is. It's a sequential model. It's a feed forward neural network. Uh, so this is how you define it. You can look it up in the documentation for the TensorFlow. Yeah, in the tutorials you will have a bunch of stuff. Here we have another classification problem. You can look it up later. But yeah, in our case, we're going to be using a neural network that does all this. This is the architecture of our neural network. So I think we did this. Now, if we look at our summary, model dot summary. Yeah, here you can see it. So the total number of parameters that we're going to be training is 11,075. Okay, and this is how much data it's going to take. Not data, sorry, storage space is going to take to store all these, to train all these. And yeah, so where do we do all this? So how do we get to this trainable parameters thing? Since we have 128 neurons in this layer, the next layer is 64. So you have 128 into 64 different weights, right? So if we look here, images. Yeah, see here 1, 2, 3, 4, 1, 2, 3, 4. Each neuron is connected to the other neuron. So you have 4, 8, 12, 16. I mean, these are not all connected to each other. Here, yeah, 4, 8, 12, 16. You have 16 trainable parameters here. There are 4 into 5, you have 20. And then when you keep adding this up, you get all of your parameters together. So that's what it is. Now, next. Now you compile your model. So the metric you're looking for is accuracy. You use something called an Adam optimizer. It's sort of like gradient descent, but it's a lot easier. It's a lot more efficient than gradient descent. You'll once you want to actually research on your types of optimizers, Adam is sort of the best out there. I mean, don't quote me on that, but Adam is generally what's used in most of these neural network applications because it's the most efficient form of gradient descent. I mean, if you look at Adam optimizer. Adam optimizer is an optimizer. Adam algorithm. Adam optimization is a stochastic gradient descent method that is based on adaptive. This is a lot more advanced. You don't have to know this right now. I mean, there are other algorithms that sort of emulate Adam, but so far Adam has been the best. Yeah, like you have RMS prop, SDG, Nesetrov, you have ADA delta, and you have Adam, right? Yeah. Anyways, quick little tangent. Let's not open that again. But yeah, Adam is our optimizer. This is the gradient descent part of it all. This is how the backpropagation will happen. Then you monitor. So now this is our early stopping callback. So what I realized when I was actually preparing for this was that it kept hitting a same accuracy level and it wasn't increasing further. So just to save time, once your accuracy sort of gets stuck at a certain level, instead of changing the architecture around, you can add a callback function. So the callback is essentially stop training once it sort of hits that I don't know what you call it, deadlock. I don't know it's a deadlock. I don't know what the word for it is, but once it hits, keeps hitting the same accuracy level, it stops the training. Dead end, dead end. That's the word. I was thinking. Yeah. Okay. Now you train the model. So model.fit. That's what we were talking about last time. So essentially, in the linear regression thing, you were trying to fit a curve on all your data points, so your error is the minimum. That's what you're doing here. So you're gonna run it 100 times. You're gonna run 100 loops all over your data set and try to see if it's getting better. So you use your xtrain, your training data, your training labels, you add your callback and your validation. You will validation you'll see later. I mean, once you start actually researching all this. So we try to fit. Whoops. Fit. Oh no, you must compile. I am an idiot. Okay. Please run. Yeah, thank God. Yeah. Okay. So what's our accuracy? Yeah. Okay. So our accuracy sort of stops at around 96, 99, whatever. And now we check it against our test data, right? What is our test loss? What is our okay? Surprisingly long time. What is happening? This shouldn't take that much time, but I don't know why. Okay, while that happens, I guess we look at horrible comments. Oh, okay. Never mind. Thank God. Yeah. So we have a test accuracy of 93%. Wow. Our classifier has S grade. Fantastic. Now we can tweak some values around. We can change this. Like, okay, this is a regularization. This is what I was talking about here. Regularization is essentially a way to stop overfitting. Yeah. So regularization is the act of changing a situation. No, not that regularization. Sorry. Regularization in ML. Yeah. So I think I explained overfitting in the last session. Overfitting essentially means when your model is too generalized, right? Here, our model is going wacky. This is fine. Like you let a few go. Once you add new test sets, it won't really perform that well. And this underfitting thing is just awful. So regularization essentially prevents that. You don't need to know the maths, right? Oh my god, it's still training. Sorry. Yeah, regularization essentially means to minimize overfitting and underfitting. Dropout, we had to talk about. So dropout layer. What does a dropout layer do? Dropout. My God. Dropout layer is again to prevent overfitting. Now, why am I focusing so much on overfitting and underfitting? Right? Because our data set is so small, and I mentioned before that neural networks sort of need a lot of data. So to fix for that, we are going to be adding a dropout layer. You can read up on all of this. There's a bunch of resources out there if you just Google like deep learning books. You'll get a bunch of resources, and I particularly like this book, Deep Learning. I think I have this. Yeah, this is a great book. I've been reading this a bit. It has all the maths behind it. Like, let's see, regularization and under constraint problems. This is actually good for my research work. But yeah, there was regularization. Yeah, so you can go through all this fun math. This is great. Oh, yeah, this is eigen decomposition, guys, by the way. This is very fun. You should go through it later. But yeah, I'm getting sidetracked. I'm sorry. Yeah. So, oh, cat. Yeah. So we've added all this just to sort of stop it from generalizing, right? Stop it from generalizing too much. This is what a model looks like, blah, 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 blah. And we've achieved accuracy on our test set. Test meaning stuff that the model has never seen before. On our test set, we have an accuracy of 93. Now, if we actually remove the callback, let's say we don't use a callback, that means we don't do early stopping. I'll show you that as well. We remove this. We don't need this. It will go through all 100. And look, accuracy here is 100%. Wow, fantastic. But it might mean nothing has changed. So, it's better to just prevent overfitting. I don't think the early callback matters. I think in a previous method, I don't know why I added it. But in usual cases, it's better to add a callback function just to keep, once you deploy in production, it's better to have a callback function once you're training. Anyways, yeah. So that was our 100 epochs. We can run it for like 1,000. I don't think it would matter. But yeah, let's run it for 1,000 epochs. Let's see. Epoch essentially means like a training step, right? Like you run it thousands of times. Oh yeah, I forgot how much I have to scroll for this video. As you can start to see in this part, that accuracy sort of starts bouncing around one. Yeah, then the accuracy sort of gets stuck. And there's no real point in running that many uh, epochs. Once you've reached one, you can sort of stop. So I'm just going to stop this right here because I do not have the patience. Yeah. So you saw 1,000. Let's just get it back to 100. Yeah. That's nice. 14 was enough to get 100% accuracy. And we're still at 93. Fantastic. So if you can mess around with these values, I guess. What if we did that? So drop out the 0.3 and the 0.01. These are all hyperparameters, parameters that you have to mess around with yourself to figure out what's going on. Summary, this is okay, this is fine, compile, and okay. Yep. Okay, 99, that's not bad. But yeah. And our accuracy stays the same. So you can mess around with it how much you want. And yeah. Okay, so that was classification with iris dataset. Now let's move on to the big stuff. Let's move on to classification with BERT, sentiment analysis. Oh, oops. Sorry, didn't mean to do that. Yeah. Anyways, sentiment analysis with BERT. What does sentiment analysis mean, first of all? Then we look at what BERT means. Yeah. So sentiment analysis essentially means whether a sentence is positive or negative, right? Whether I'm saying nice things about you or I'm talking shit about you. Yeah. So we can even run this now. So here I'm actually using a GPU. I was doing something for 2 hours on a GPU. I can't remember. But yeah, let's run this and see. So while that is running, BERT stands for bidirectional encoder representation transfer. I'm sorry. Am I missing some values? BERT and as oops. Huh. Yeah, okay. Well, I don't know where that went off, but yeah. So, okay. Anyways, yeah. Okay. So this is our sample data set. This is what we see. This is one of our uh, values, one of our reviews. So a bit about the data set itself. This is the IMDb data set. Okay. So the IMDb reviews data set. Essentially, what this is you take a bunch of movie reviews, then a human or a bunch of humans will go through it and say that okay, this is a good review, okay, this is a bad review, good, bad, and then put it all in a data set, and then we can use this data set to essentially predict whether a review will be good or bad. Okay, we ran that already. Okay, so we'll use something called the Transformers library. Transformers library. It's not the Optimus Prime. Transformers is actually a very important library when it comes to natural language processing. Oh my god. Deep learning. Right. Transformers deep learning library. Yeah, so Transformers, state of the art machine learning for PyTorch, TensorFlow, JAX, blah blah blah. Transformers essentially gets us the Transformers algorithm. Now, the Transformers algorithm is a very important algorithm. Most of all NLP tasks, like LLM. So if you know ChatGPT is based on an LLM. Our next session will actually be handling LLMs. So yeah, ChatGPT is based on something called a transformers. ChatGPT is based on LLMs. LLMs are based on something called a transformers algorithm. So transformers was released by Google. Transformers deep learning algo. Algo. Okay. And there's a very nice paper based on the algorithm. It was released by Google. Paper. If you'd like, you can read it. It's titled Attention is All You Need. Here's a paper. You can go through all the maths and everything. I mean, great paper once you start to understand the actual meanings. This is the architecture. Look, you can see here it encodes. So it has attention mechanism, self attention, and positional encoding. You can read about that later. We don't have time to explain transformers right now. But yeah, so now you import your model from the transformers library, right? We're doing something called transfer learning. Transfer learning essentially means someone made a big model a long time back or like recently. And now you're just going to take that model, whatever the saved version of that model was, whatever after training that model, you took that and then you extended it based on your own use case. So that's what we're doing here. We're going to take this model, the BERT model, and we're going to extend it for our own use case. So if we run it, I don't know why these take so much time. It is working. Oh, okay, yeah, you got to download. Okay, this model is considerably bigger than ours, as you would expect. But yeah, cool. Model.summary. Man, why is it so slow today? Yeah, okay, this is your model summary. And here you can see considerably bigger than our old model. Okay, like our model, just for this tiny little data set, had where was it? Model summary, right? Yeah, our model had 11,000 parameters, trainable. 11,000 parameters. Pretty modest, you would think. Like, imagine an equation with 11,000 coefficients, right? That's what this is. And you'd think 11,000 is big. But this model has, what is this? 109 million parameters. And out of that, most of them are not even, most of them are trainable. Okay, yeah. So all of them are trainable, just like last time. And yeah, so this is our sort of extended version. We'll make our extended version later. But yeah. So considerably bigger model with a lot of more features. It's a lot better model than whatever we were trying to do. because it's for a better use case. This BERT model also, by the way, made by Google. So shout out to Google, this small up and coming startup. Yeah, so this is just a utility function. This, like last time, we're turning whatever the text value was. So even here in the data set, you can see it's given in text, right? You need to turn it to a number. So since we have only two classes, you're going to do 0 and 1, and that works out fine. You don't need like 3, right? You don't need 3 bits to represent two values. 1 bit is enough. But yeah, even in our data set, we have 45,000 reviews, which we're going to convert to uh, numbers. But yeah, okay. So now let's move on to tokenization. Okay. Now, here's where I was talking about converting words to numbers. Okay. So, in its own vocabulary, tokenization essentially converts each word into a numerical representation where it's either splitting up a word. Okay, this is distracting. It's either splitting up a word or it's giving like each word a number. So, in is 1999. This is 2023. K is 10,556. And then the rest of Kaggle. Like in this sentence, you can see. In the sentence, you can see uh, KA, notebook, I will, blah, 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 blah. All right. And yeah, this bird has a vocabulary of 30,000 tokens. So 30 different types of tokens can be analyzed in this. And you can go through the library. This later, I've added a bit of documentation. Like there is a bit of documentation in this. Okay. Yeah. So this is another utility function. You can go through this later. The links are there for this, I hope. I had sent it before. But yeah, okay, cool. So now you have, this is our first example. One of the other reviewers mentioned that, blah, 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 blah. Whatever this is. We don't care about the actual innards of the data just yet. We just care that the data is there, the data is clean, and it's ready to be usable. So now this function essentially converts it to a data set that TensorFlow can actually use. Right? This is just a utility function. You don't need it right now. Okay. Utility function, you can see is just a bunch of specifications I've added. We don't need to get into the details of this right now. But yeah, so you run this actually. Yeah, run this. Whoops, why did I not run? Huh. Okay. Scikit-learn is great until it isn't. Okay. Yeah, so now it's going to convert everything into the tokens. And that might take some time because that's a CPU task. While this runs, we will, I don't know, chill for a bit. I mean, I've already added everything. Yeah. So I've added a few of my own sort of reviews and then tested it against the model and we get an accurate prediction. Negative, negative, negative. Yeah. Anyways, going back, I'm hoping this is going to take some time. This is going to take like 5 more minutes. So until then, what do you suggest we do? Because I don't know. There's 12 people here. I don't know. What do you guys want to do? Because this is a lot of machine learning. Giving you spoilers right now, but yeah, a lot of machine learning is just going to be you waiting around for either the model to train or the data set to get downloaded. Especially in like VIT Wi-Fi, downloads take a hell out of time. So usually I just go back home and download whatever I need to, and then come back and work on it because data at home is considerably faster. But yeah, so we're gonna wait for this to happen. Essentially, in this step, you're converting everything to tokens, and then you convert everything to a data set that TensorFlow can use. That's all that's happening here. So if anyone from GDSC is watching, just like Text me, tell me, give me feedback, give me. Oh, now I can actually go through the comments. Yeah, let's go, Sid. Let's go. No, you're watching. Hmm. Okay, this is getting extremely boring. I feel like we should do something more fun. This was fun, I guess. Uh, there was some AI game somewhere. Google AI experiments. Experiments with Google. Yeah, these are AI experiments. So while that trains, I guess we can goof around with this. 14 years, 16, 13. Okay, stop boasting. Yeah, AI experiments. Let's go here. Instrument playing, passing of water. Okay, what did I do? Oh no, back. Yeah. Mm-hmm. Test blue light. Actually, you know what? Let's go through the other TensorFlow stuff because we should be productive and not get distracted. Oh wait, yeah, no, I'm getting distracted. I'm sorry. Oops, oops. Okay. So here is the sort of hello world in TensorFlow. Quick start for beginners. You can go through this. Essentially, what's happening in this example, they're using something called the MNIST dataset. Okay, the MNIST dataset is a dataset of images of handwritten digits, and you're going to classify those handwritten digits using a neural network. So you build a machine learning model. That's what you're doing here. Sequentially useful for stacking layers, blah blah blah. Flat, dense, dropout layers. We already saw this. Predictions. You set predictions. You get this. Blah blah blah. Okay. You can read through all of this very succinctly put once you can actually understand the maths. Yeah, this would be the first one, handwritten text classification. If you want more resources for machine learning, you can. This is what I used to use, Raj. This was a great YouTube channel. This YouTuber, he looks very goofy. That's why I like him. But yeah, Siraj Raval is great for machine learning. Yeah, like AI sports betting bot. This is all good. This is how I started learning machine learning. Let's go back. Yep. Okay, this will happen. Never mind. So you can go through all this, building a trading bot with ChatGPT. Very clickbaity, but yeah, it's good. This is a great tutorial. TensorFlow in 5 minutes. This is not true, by the way. TensorFlow takes a whole lot more time. But yeah, good for clickbait though. Learn machine learning in 3 months. Huh? How to predict stock price. Okay, we did this one last time. Nice. Introduction to data science. Blah 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 blah. This is great, by the way. This is a great channel. Another channel that's very good for machine learning is StatQuest. StatQuest is great. You can go through StatQuest. This guy is great because he explains the maths of everything. So if you look here, yeah, PCA. PCA stands for Principal Component Analysis. Essentially, it's for dimensionality reduction. Here's logistic regression, what we talked about earlier. K means clustering. This was that unsupervised learning. ROC, God, I forgot what ROC stood for. But yeah, this is also important for metrics and evaluating your model. Linear regression, clearly explained. This is what we did last session. This is probability stuff, support vector machines. We talked about this earlier in our session. PCA again, gradient descent again. And this channel is great. So I recommend going through this channel as well. Then, what am I subscribed to? Yeah, I mean, IBM Technology has some great tutorials. Like you can see, this is just like general development stuff, but there's other stuff as here as well, like generative models explained, AI versus machine learning. What's the difference between AI versus machine learning? So AI sort of is a blanket term. Machine learning is more specific, like you actually apply the maths and everything. Containerization, if you want to learn Docker, you can either go here or you can go to our old session about Docker that I took last time. Anyway, so you have Kubernetes, machine learning versus deep learning. We went through this today. Blah 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 blah. Kafka is great. Yeah. So this is also a great, great channel. Let's go back. Yeah. Oh, thank God, it's done. Cool. Okay, this is only 5K. We can just sort of stick around here. After that is done, this will take more time because since we have 50,000 movie reviews and only one measly GPU, this will take a whole lot more time. But yeah, okay, we are 40% done. Anyways, let's go back to YouTube. Another good channel, 3 Blue 1 Brown. Three. If you don't know 3 Blue 1 Brown, I am very sorry for you. 3 Blue 1 Brown is great. Neural networks. Neural networks. Yeah. Here you can see 3 Blue 1 Brown neural networks. Blah, blah, blah. Okay. Cool. 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 Yeah. See. What is deep learning? Gradient descent. Fantastic video. One of my favorite videos of all time. Back propagation, what happens in back propagation, stuff like that. There's convolution. So convolution is important for convolutional neural networks. Convolutional neural networks essentially are for image classification. Convnets. Convnets. Convnet is made of layers, every layer, blah blah blah. Convolutional neural. Here's what I wanted. Yeah. A type of neural network that can be affected. Oh, okay, it's done. But yeah, convolutional neural network. Oh my God. Convolutional neural network coordinates as CNNs is a type of neural network effective for image recognition and classification. So, if you have an image data set later, we can actually use this. Okay, anyways. So, now let's train the model. This will take a lot of time. So, I'm not going to train it fully. I actually have a trained version already saved here. Right? I hope. Okay, no. It got deleted. Never mind. But yeah, so this will take some time in training. And we don't want that. Yeah, look, already already accuracy is at 1 because I trained it before and I think it got saved in memory. Huh, I don't know what happened, but yeah. So already loss is very low, but what are you gonna do? So I think let's leave it for like 5 minutes. It just usually takes like 2 hours to get trained at least. If you can see here, our GPU usage has gone way up because we are actually now using the GPU to train everything. Our GPU is pretty great actually. We have 16 GB of VRAM or whatnot. We have 29 GB of RAM here. This is fantastic. But yeah, so I recommend using Kaggle for your machine learning stuff because you get your GPU for free. Colab usually sort of crashes, and that's not nice for anyone. But yeah, if you stop, yeah, if you stop this, it'll throw an error. But now you can actually spread sentences, not oh, oops, spread sentences. You can now actually predict shit. Yeah. And it's gonna mess up a little bit. Blew my mind. Yeah, that's not right at all. But yeah, so you need to let it train. Once it's done training, you can actually start predicting stuff. Right now, it's doing very badly because it's not trained yet. Once it's done training, you can try it on your own. This you can run anytime. So here you can actually set when to run this whole Jupyter notebook. So it'll train on its own once the trigger is there. And yeah, so unfortunately, we don't actually have time to just wait around and let it train. So I'm gonna leave it to you to sort of see how it goes. Okay. Um, okay. Actually, our loss is very little now. What if I stop this? and do it again. Sentences. Okay, never mind. Yeah, it's still bad. Like this is positive, but it's still showing negative. So something's wrong because we didn't let the model train enough. Anyways, so you can try this yourself. Once you do, it will give you a result. I mean, if we set sentences equals I loved the movie. It blew my socks off. Then run it. Oh, why is it not? Is it using the old? Huh, that's weird. Wait, this is weird. Bread sentences. We put here. List index out of range. What are you talking? Oh, label I. Yeah, I don't know what's wrong with this. I think it's because I stopped this from running. So now it's sort of all off. Huh. This is very weird. I don't know why this happened. Bread sentences. Okay. Yeah, look, it's still very, very bad. If I did like. Yeah, I know. Thanks, man. Good movie. Yeah, okay. It's still very bad because we didn't let it train. So once you do actually let it train, I should have trained it before, but my I actually had saved the model so I could use it later, but Kaggle messed up and deleted my model. I mean, Kaggle didn't mess up, I messed up, but yeah. Anyways, so we'll let that train. I mean, I'll let that train, and then you can look at the repository results later. And yeah, so if anyone has any questions, let me know. I'm sorry to end the session at this note, but we're running out of time. 1.5 hours is more than enough for this kind of stuff because it's either like a 6 hour session where you go into the details of the mathematics, or you have like 1 hour where you glance over everything and then you sort of leave it to the reader, leave it to the viewer as an exercise to go further and actually explore everything. So this library, this notebook sort of serves as a reference to everything else. And yeah, if there are no questions in the chat, uh, I will be ending the session. Any questions? I will wait for 1 whole minute. Oh, okay. Abhay is still here. Oh, okay. I'm sorry, I couldn't see the comment before. Oh, Abhay is still here. Fantastic. I've done some machine learning model project. Oh yeah, diabetes prediction. Yeah, that's a good project. So, Abhay, if you want some ideas on projects, you can simply go to Kaggle, pick a random data set, and then just do stuff on it. Begin it. Take the Titanic data set, take the housing prices, spaceship Titanic. That's pretty cool. Uh, oh, hey man, Kostov, what's going? Yeah, you can go through competitions here. Um, so you can do a bunch of stuff with machine learning, especially now that you have like a bunch of APIs, ML APIs, powerful ML APIs. Essentially, if you have like cloud access, you can even train your machine learning models on AWS. I see that you are using Windows. Uh, yeah, so you only use Windows, which is, I mean, I don't use Windows. I'm currently using Linux here. It's a lot more fun. What is? this. I don't know what I was doing. Neo fetch. This is my Linux thingy. Yeah, so if you can see here, it's a pretty decent laptop. I like it because I can do machine learning on it. This is my GPU. This is how much memory I'm using. And Ubuntu is great. If you'd like, I recommend everyone to use Linux. I mean, not everyone, but if you're a programmer, I believe in Linux supremacy. I particularly despise programming on Windows because just no. Yeah. So, anyways, yeah. So, ideas for projects. You can go to Kaggle, or you can straight up just Google it. You know, ML project ideas, or once the GDSC recruitment start, you can ask us, and we'll give you some ideas. Right, guys? Mm-hmm. Okay. Anyways, yeah. So, deep learning projects. Just Google anything and just start it. That's my recommendation to you. Anyways, no more questions. I hope. I hope not. I don't know. Yeah, get Linux. It's great. You love it. Okay then. That's it then. That's it from me. Let's end the session here. Bye bye.